right, so this week we introduced these problems around differential equations. So I just want to give a high-level overview and review of what we encountered here. Before this, we'd been interested in finding derivatives. Given a function, find me a derivative, right? And then doing different things with the derivatives of those functions. So we had a couple of different kinds of functions, things that were polynomials, things like x squared, trigonometric functions like sine of x, and exponential functions like e to the x. All right, and we found derivatives of these. We found combinations of derivatives of different kind of products and things, but it was all about finding derivatives. So this week we kind of changed our perspective, or one way to think about this is a change of perspective in the kind of questions that were asked. Rather than being given a function and told what the relationship is, now we were looking at situations where we were given information about a derivative and asked to speak to something about the original function, the function who had that derivative. For example, maybe we were told instead of that a function is x squared or sine of x or e to the x, that a function's derivative is x squared or the sine of x or e to the x. And we started to look at that just based on inspection. You know, like with some of these examples, it's not too hard to come up with a function who has x squared as a derivative. For example, anything that looks like x cubed over 3, right? Just our basic power rule. And we can check this, that the derivative of x cubed over 3 would be 3 times x squared, right? If we want to just write this here, 3 times x squared divided by 3. So those guys go away, that's x squared. And that means that this solves that equation, right? If this is f of x, right, then that solves this equation because the derivative of f with respect to x is x squared, and x squared does equal x squared, okay? So we are finding a solution to an equation. Same thing with this function, g of x. Instead of a function who is defined as the sine, some function whose derivative is the sine. And if we think about whose derivative would be sine, well, the cosine's derivative is negative sine, so we would look for the g of x equals something like negative cosine of x. But in these two examples, we can dig a little bit deeper, because maybe you notice that not only does x cubed over 3 solve this, but so would something like x cubed over 3 plus 2. So would something like negative cosine of x minus 10. Because the derivative of this term and this term, right, of any constant would be 0. So you would still have a solution to your equations. And here we have e to the x plus, again, any arbitrary constant. So rather than a single solution to these differential equations, what we're faced with is we're faced with multiple solutions, an infinite number of solutions. Any constant value plus e to the x, any constant value plus negative cosine of x, any constant value plus x cubed over 3. And not only this, but maybe we recognize, we talked about recognizing a connection between the solutions to these differential equations and things that we've done before. Namely, that when we solved this expression, we got x cubed over 3. And we've seen a relationship like this before. We saw a relationship like this when we were doing integration. And in fact, this is just a different kind of a way to interpret that operation of integration, or the thing of an integral. And that's through an indefinite integral. And so we can also frame a problem like this, df dx equals x squared, as solving this indefinite integral. That we just don't have limits here. But what function has one way to interpret this is, what is a function whose derivative is x squared with respect to x? And that's anything that looks like x cubed over 3 plus or minus a constant.